Recall the, recall the initial value problem that we already solved in earlier lectures. It's right here. We said this was the solution, right? So we're going to try to estimate it with Runge-Kutta. This is a volatile kind of curve, so we said the other methods didn't really do that well. Let's see if this one does better, okay? So I'm going to try to solve this numerically by using the Runge-Kutta method over the interval 0 to 9 with h equals 1. All right. So let's go to our Excel. We're going to program with Excel. So here's my i's, 1 through 10. Here's my x sub I, 1 through 0. Here's my 4 slopes, x1, x2, x3, x4. Okay, and then here I have my function. So for the first slope, b2 is the x value, and then c2 is the y value. For the first slope, it's just the big F evaluated at x sub naught, y sub naught, right? So I'm just going to put that here, and I'm going to put an equal sign. So the first slope is just the function evaluated at x sub naught, y sub naught, okay? The second slope is going to be the function evaluated at x sub naught plus h divided by 2. H is 1, so h divided by 2 is 0.5. And then instead of y, I'm actually going to use, right here, instead of y, here, let me make it in red. I'm actually going to use Euler's approximation of y. So c sub 2, existing value of y, plus d sub 2, which is the slope, the first slope, plus 1/2 h, right? Because we said it's gonna be 1/2 h, 1/2 h, 1/2 h. Okay. All right. So let me copy that. That's the second slope. All right. So equals. All right. I'm gonna drag this down. All right. The third slope. Here's the code for it. Same thing, but the only difference is y is going to be estimated by using the second slope, e2 instead of d2. Okay, but the code is the same. All right. So I'm gonna put that here. All right, here we go. The fourth slope. Oh my, I know. There's codes on this for this online. So if your professor is torturing you, you can just Google like C++ Runge-Kutta for code or something. Okay, so that's the fourth. And then notice what we did here. It's back to being +1, right? Because it was back to being plus h. And then the error is this. The error is the same as in the previous codes. We'll take the absolute value of it. Okay. All right. And then, okay, so y sub 1. The first value is 6.5 equals. The second value is previous step plus h, which is 1, divided by 6 times the sum of the first slope plus 2 times the second slope plus 2 times the third slope plus the fourth slope. All right, here we go. Let's do average error for our notes. All right, here we go. All right, this does not look good. Look at these y values, right? This does not look good. We know our y values kind of stayed between two values, but these do not look good. So let's actually take a look at what it graphed as. So these are my estimations. The average error was 62.07, and this is what my graph looks like. Looks like it did an even worse job than Euler's or improved Euler's did. And again, the reason is because if you turn that corner too soon, it looks like it throws you off the graph completely. So let's do the same thing, but by using more smaller values of h. All right, so let's use h equals 0.5. I'm not going to go back to Excel for this one. I'll just tell you the results. For h equals 0.5, you get something like this. So just, okay, so h is 0.5. Your error is 2.7, so not bad. So actually put 0.05. If you remember, for Euler's method, it was actually all over the place. Still, this one, it's not, it's kind of tamed. And then we'll do h equals 0.2. So for h equals 0.2, you already get a really nice result. And the error is 0.326. Okay. So that's Runge-Kutta. Just h equals 1 is too small for too large for this problem, so it feels like it doesn't matter what method you use, it won't be able to do it. So 0.2 is probably the best value. All right. The last thing I'm going to do is compare the errors for the numerical method. So Euler, improved Euler, and Runge-Kutta of order 4. For h equals 1, Runge-Kutta actually Euler's did the best for h equals 1. Improved Euler and Runge-Kutta did worse. That's actually just a glitch. And the reason is because I said that the curve turns, and it looks like if you take a turn at the wrong spot, it actually throws you more off the curve. And it looks like for Euler, it took the turn at a better spot than for improved Euler's and Runge-Kutta. For h equals 0.5, the error for Euler's got bigger because now I think what you're doing here is you took the turn at the wrong spot here. But for improved Euler's and for Runge-Kutta, it got smaller. And for h equals 0.2, for the errors got smaller, but it looks like for Runge-Kutta, the error is getting smaller faster than for the other ones, right? But the best method is Runge-Kutta for h equals 0.2. Okay. Error analysis is a big part of numerical analysis. That's where the theory comes in. The big question is how do you know how far off you are the right answer if you don't know what the right answer is? That's what the topic called error analysis and stats and numerical analysis. It is very, I mean, you have to understand Calc 1, Calc 2, and Calc 3 to understand it. So that's kind of the part where our hands are tied. But I'll tell you the summary. So Euler's method is said to have error of order h. What that means is halving h will roughly halve the error. We don't see that here because this is a volatile function. I think you'll see that better on your homework problem. But this is the general rule, right? So if something is of order h, it means if you have the interval h, you'll have the error in general. For this one, it doesn't seem to work that well, but at least we did go down. The error in improved Euler is of order h squared, which means if you have h, you will roughly reduce the error by 1/4, right? So it kind of worked here, I guess. We have to kind of half the error. We did more than half it, right? So the error got more, yeah, the error got down by 1/4. But again, it says approximately. So the more well-behaved, less volatile the function is, the more predictable it is. And then the error in Runge-Kutta is of order h to the 4th. That means if you have h, you will roughly reduce the error by a factor of 1/16. Or 1/2 to the 4th. And you can that would explain the more dramatic drop here, right? Because look, you have to go from 8.75 to this. You went, yeah. So that explains the more dramatic drop for Runge-Kutta. Okay. I'm going to give you a chance to practice the Runge-Kutta method. And then I'm not sure what the last lesson will be. Maybe we'll do it just another application, kind of pulling everything together. Because the other numerical methods, this is pretty much as far down the rabbit hole we can go without things getting insane. Just kind of introducing the different methods and observing that the error is different for all of them. So to go further, you'd have to do a little bit of error analysis. You have to pick up on programming and stuff like that. Okay, so maybe just applications for the last lesson, but I'm just going to let you go back to that one homework problem. Just redo it with Runge-Kutta and see what happens, okay? And there's Runge-Kutta methods of different orders. So you can have RK8, RK16, whatever. The only problem is the more steps you have to do, the longer a computer has to think. I know it doesn't seem like a huge deal when you're just using Excel, but that could be, the time it takes to compute something actually becomes an issue when you're doing real world problems. And the most time consuming thing is evaluating this function, big F. That's the most time consuming thing. Okay. All right, I'm going to let you try to program Runge-Kutta in Excel.